All right, so in this segment, we're going to keep exploring solutions, and we're going to look at how the solutes affect the properties of the solution compared to the pure liquid. So we'll be examining the dependence of vapor pressure on solution concentration. We'll explain why solutes can lower freezing points and raise boiling points, and actually calculate the boiling point elevations and freezing point depressions, and define ideal solutions and explain deviations from ideality in Raoult's law. So this gets to a concept called colligative properties. And colligative properties are properties whose values depend only on the number of solute particles and not on what they are. How could a property depend um, not just on the number of solute particles? Basically, what we'll discover is that these are properties that are dependent on the concentration of the solution. And if it depends on the concentration of solution, it doesn't really matter what the solute particles are, just how many of them there are and how that affects the solution concentration. So yeah, the value of the property depends on the concentration of the solution. The difference in the value of the property between the solution and the pure substance is generally related to the different attractive forces and solute particles occupying the solvent molecules' positions. So let's revisit the vapor pressure of solutions to understand how solutes might change that. So you have an enclosed container and you've got a dynamic equilibrium going on. Uh, um, uh, you've got molecules reaching high enough kinetic energy, escaping from the liquid into the vapor phase. And every now and then, a particularly cool molecule in the vapor will stick onto the liquid and go into the liquid. Okay. So the vapor pressure of the solvent above a solution, and this is key, is lower than the vapor pressure of the pure solvent. Because the solute particles replace some of the solvent molecules at the surface, and the pure solvent establishes a liquid equilibrium. Um, but if the solute is replacing that, the pure solvent establishes the equilibrium. The solute being present is going to reduce the number of molecules that can go up because you have a smaller fraction of molecules that are escaping. So the rate of vaporization is reduced by the solute because there's less solvent there. It's only partly solvent, and so only the rate that it escapes is lower. There's less solvent per unit area. And so if equilibrium eventually gets reestablished, you still have the same rate of molecules coming back in, but you have a lower rate of molecules going out. So the dynamic equilibrium is established with a lower vapor pressure. Yeah, the vapor pressure will be lower. So this gets the idea of a thirsty solution. A concentrated solution will draw solvent molecules toward it due to the natural drive for the materials in nature to mix. Similarly, a concentrated solution will draw pure solvent vapor into it in this tendency to mix. The pure solvent vapor will want to go into the mixture. Um, yeah, so later classes in thermodynamics will make this all much more quantitative. But for now, the basic idea is a solution is more stable than a pure substance, and because of the mixing. So an example of what a thirsty solution is, a solution that wants more water. So let's say we have a pure solvent and a pure solvent and a concentrated solution sitting in a container so that they share the same vapor pressure. So as you let it go, you get evaporation off both of them, but there's more evaporation off the level of pure solvent. But the atmosphere, it's the same vapor pressure overall because it's mixing. And so the rates going on will be the same, but the rates coming off the pure solvent will be higher. So the net effect will be a transfer of solution from the pure solvent, a transfer of solvent molecules from the pure solvent into the solution. So when the equilibrium is established, the liquid level in the solution beaker is higher than the solution level in the pure solvent beaker. So to understand this a little bit more, I'm going to get quantitative. We're going to cover Raoult's law. So Raoult's law is that the vapor pressure of a volatile solvent above a solution is equal to its normal vapor pressure multiplied by its mole fraction in solution. So we'd write that as the vapor pressure of the solvent in a solution is going to be the mole fraction of solvent in the solution divided by what its vapor pressure would be if it was pure. And so because the mole fraction is always less than 1, the vapor pressure of the solvent in solution will always be less. So vapor pressure lowering, so the vapor pressure is always going to be lower than the vapor pressure of the pure solvent. The vapor pressure of the solution is directly proportional to the amount of solvent in the solution. And so this difference between what the vapor pressure of the pure solvent would be and the vapor pressure of the solvent in solution is called the vapor pressure lowering, right? It's just that change in vapor pressure. So yeah, so our delta vapor pressure is just our change in the vapor pressure of the pure solvent itself minus the vapor pressure of the solution is going to be equal to, now this is important here, when labels get switched, things get confusing. This is the mole fraction of the solute times the pure solvent, right? Because if you look at this, this is P star solvent, and this is P star solvent times mole fraction solvent. So we factor this out, we get pure vapor pressure solvent times 1 minus the mole fraction of the solvent. But assuming it's just yeah, so we can lump, because it just matters of about the concentration of the solvent, we can actually lump all the solutes together. So if you take the total mole fraction of all the solutes, that is exactly 1 minus the mole fraction of the solvent. So this equals P0 mole fraction solute. So that's the thing to watch out for. In any of these problems, be very careful about the labeling. Is it is a mole fraction the solute mole fraction or the solvent mole fraction? You can always convert it back and forth very easily as long as you know which one it is. Okay. Example, the vapor pressure at 25 degrees C of a solution containing 300 grams sucrose, it's a fair amount of sugar, and 300 milliliters water. The vapor pressure of pure water at 25 degrees C is 23.8 torr. Assume the density of water is 1 gram per milliliter. Okay, so what we want to do is figure out the mole fraction of the solution, of the solvent, the mole fraction of water. So to do that, we need to figure out the moles of all the components. Well, let's see. We've got 300 grams sucrose, and I won't bother calculating the molar mass here, but it ends up being 342.3 grams sucrose per 1 mole sucrose. And you get 0.877 moles. We have 300 milliliters of H2O, and we have, for 1 milliliter, we have 1 gram H2O. That cancels. And then we have 18.02 grams H2O per 1 mole H2O. And that gives us 16.65 moles. So the mole fraction of H2O, and that's not an X, it's a Xi. That's what's usually used in mole fraction, but you can write an X as well, that's fine. Is 16.65. This is important, we're interested in the mole fraction of solvent. Divided by 16.65 plus 0.877, which is 0.950. It's by mole, it's 95% water. Now this is interesting because in this case, because sucrose is so much heavier than water, you actually have by weight, about equal amounts. But by mole, you have 95% water. It's interesting, this is actually only about half the solubility limit of sucrose. You can just dissolve a lot of sugar in water. So yes, surprisingly, although it's about 300 grams of each, the mole fraction is 95% water, 5% sucrose, because you've got a few big sucroses and lots of waters. Their mass is about equal, their numbers are not. So our pressure is going to be times C solvent, which is going to be 23.8 torr. This is a fraction thing, so whether it's torr atmospheres, that doesn't really come into play at all. We don't really need to do any conversions. was 22.6 torr. So you only get a slight lowering in the vapor pressure, despite having such a large mass of both sugar and water.